Imagine a world where you never have to charge your smartphone again, where pacemakers last a lifetime, and where satellites operate for decades without power concerns. This isn't science fiction, it's the promise of nuclear diamond batteries.
Now, radiovoltaics are the ones that we specialize in. They act much like a solar panel, except instead of harvesting photons,
Batteries, poised to enter the market in 2025. Now, radiovoltaics are the one.
Particles from radioisotope decay. So in the case of tritium, the half-life is about 12.3 years, which means that after 12.3 years
that we specialize in. They act much like a solar panel, except instead of harvesting photons from the sun, they harvest particles from radioisotope decay. In the case of tritium, the half-life is about 12.3 years, which means that after 12.3 years, these revolutionary power sources combine radioactive waste with mankind's hardest material to create something extraordinary, batteries that could potentially last thousands of years. I think for the first time in the history of nuclear batteries, they are at a place where they may be commercially relevant, meaning that the cost can be low enough, safety can be high enough, and the power density is relevant, along with a scalable cost point. As we stand on the precipice of this energy revolution, let's explore how these tiny powerhouses might soon transform our world in ways we've only dreamed possible. To grasp the magnitude of this innovation, we need to dive into how these remarkable batteries actually work. Nuclear diamond batteries harness the natural decay of radioactive isotopes, specifically carbon-14, to generate electricity continuously for decades, even centuries. At their core, these batteries utilize a process called beta-voltaic conversion. When radioactive carbon-14 atoms decay, they emit beta particles, essentially high-energy electrons. These emissions would normally be wasted energy, but here's where the diamond structure becomes crucial. The synthetic diamond, created from the radioactive carbon itself, captures these beta particles and converts their kinetic energy into usable electricity. Why diamond? It's not just for show. Diamond's rigid crystal lattice makes it exceptionally good at converting radiation to electricity. Plus, it's the hardest natural material on Earth, providing unparalleled durability. The diamond structure also acts as a shield, safely containing the radioactive material within. The beauty of this technology lies in its elegance.
I think for the first time in the history of nuclear batteries, they're at a place where they may be commercially relevant, meaning that the cost can be low enough, safety can be high enough.
The carbon-14 isotope has a half-life of about 5,300 years, meaning these batteries can theoretically generate power for millennia, albeit with gradually diminishing output. Even more remarkable, manufacturers can precisely calibrate the power output by controlling the amount of carbon-14 incorporated into the diamond structure. The revolutionary benefits, in the case of carbon-14, include not having to worry about doubling, because the half-life is over 5,000 years, far longer than a human time scale. But what makes these batteries truly revolutionary? The answer begins with their extraordinary lifespan. While your typical lithium-ion battery might last a few years at best, nuclear diamond batteries could power devices for decades, potentially outliving the very devices they power.
And the power density is relevant, along with a scale cost point.
This longevity creates unprecedented possibilities. Imagine medical implants that never need replacement surgery to change batteries. Nuclear diamond batteries are likely to put out significantly less power than a AA battery, but for clocks, calculators, pacemakers, and different types of sensors used in all kinds of applications, they are ideal. Think about remote sensors in hazardous or hard-to-reach locations that can operate autonomously for decades. Consider the environmental impact of eliminating billions of disposable batteries from our waste stream. Unlike conventional batteries, nuclear diamond batteries don't suffer from performance degradation in extreme temperatures. They can operate effectively in the freezing vacuum of space or the scorching heat of industrial machinery. This temperature stability opens applications where traditional batteries simply cannot function. Perhaps most counterintuitively, these batteries offer significant environmental benefits. By repurposing radioactive waste that would otherwise require expensive long-term storage, they transform an environmental liability into an asset. And once created, they produce zero emissions, no greenhouse gases, and require no recharging infrastructure. NDB Incorporated, the pioneer leading the charge in this emerging field, is Nano Diamond Battery, a company founded with the audacious goal of creating the world's first commercial nuclear diamond battery. Founded in 2012 by energy entrepreneur Nima Golsharifi, the California-based startup has positioned itself as the pioneer in this transformative technology. NDB's approach centers on a multilayered diamond structure that efficiently converts radiation into electricity while ensuring complete safety. Their patent-protected technology creates what they call a self-charging battery that can theoretically power devices for their entire useful lifetime. In recent years, NDB has achieved remarkable milestones. Their prototype demonstrations have shown stable power generation, and they've secured partnerships with several major electronics manufacturers interested in incorporating their technology. Their 2023 announcement of successful integration with a small sensor array demonstrated the battery's real-world viability. The company's business model is particularly intriguing. Rather than focusing solely on consumer electronics, NDB has strategically targeted multiple sectors: aerospace, medical, industrial, and consumer. This diversification allows them to enter markets where the value proposition is strongest, applications where battery replacement is particularly problematic or expensive. NDB's funding history reveals growing confidence in their approach. After initial seed funding, they've secured over $20 million in venture capital, including backing from prominent clean tech investors. Their most recent valuation reportedly exceeded $250 million, reflecting high expectations for their market potential. While NDB pursues its multi-layered approach, UK-based Arconlight has emerged as a formidable competitor with a distinctive technological vision. Founded by a team of nuclear physicists from the University of Bristol, Arconlight has developed an alternative method focused on maximizing efficiency. Arconlight's key differentiator lies in their isotope purification process. Unlike some competitors, they've perfected techniques to isolate and concentrate carbon-14 from nuclear waste, resulting in higher energy density batteries. Their proprietary tritium diamond technology combines multiple radioactive isotopes within a single diamond structure, potentially achieving power outputs that surpass other approaches. The company has maintained a more focused application strategy than NDB, concentrating primarily on specialized industrial applications and scientific instrumentation. This targeted approach allows them to fine-tune their batteries for specific use cases rather than pursuing a one-size-fits-all solution. Arconlight's roadmap to commercialization reflects this precision. They've established partnership agreements with several European nuclear facilities to secure their isotope supply chain. Their manufacturing facilities, currently under construction in the UK, are designed with scalability in mind, allowing them to ramp up production as market demand increases. What's particularly noteworthy about Arconlight's approach is their commitment to transparency. They've actively engaged with regulatory agencies from early development stages, participating in establishing safety standards for this emerging technology. This proactive stance on regulation could give them a critical advantage in navigating the complex approval processes that these batteries will inevitably face. Key milestones in 2024 have proven pivotal for nuclear diamond battery development, with several breakthrough moments accelerating the path to commercialization. The most significant achievement came in March 2024, when NDB demonstrated their first fully integrated consumer-scale prototype, a battery the size of a small coin capable of powering a low-energy Bluetooth device continuously for over a year without performance degradation. This shows that nuclear batteries can be made dozens of times smaller and lighter than lithium-ion batteries. Equally impressive was Arconlight's July announcement of successful miniaturization. They reduced their battery size by 60% while maintaining power output, crossing a crucial threshold for medical applications. This advancement was followed by preliminary approval from European medical device regulators to begin controlled testing in non-implantable medical equipment. On the manufacturing front, both companies have made remarkable progress. NDB unveiled their pilot production facility in Silicon Valley, capable of producing several hundred battery units monthly. Meanwhile, Arconlight completed construction of their isotope processing facility in partnership with the UK Atomic Energy Authority, solving one of the most challenging aspects of the supply chain. Academic research has accelerated alongside commercial development. Stanford University researchers published a groundbreaking paper demonstrating a new diamond lattice configuration that improves energy conversion efficiency by nearly 25% over previous designs. This technical innovation has already been licensed by several players in the field. Perhaps most crucial for market adoption, independent safety verification has progressed substantially. The International Atomic Energy Agency completed its first comprehensive safety assessment of encapsulated diamond battery designs, confirming that properly manufactured units pose no radiation risk to users. This third-party validation represents a major hurdle overcome. As technical development continues, specific applications are crystallizing from theoretical possibilities into concrete implementation plans. The aerospace sector has emerged as an early adopter, with satellite manufacturers particularly enthusiastic. Traditional satellites rely on solar panels and conventional batteries, creating vulnerability during eclipse periods and limiting operational lifespan. Diamond batteries offer a compelling alternative: continuous, reliable power for decades without degradation. In a telling development, a major satellite company recently announced plans to incorporate diamond batteries into their next generation of communication satellites, with launch scheduled for early 2025. This represents the first major commercial commitment to the technology and provides crucial validation. The medical device industry has identified diamond batteries as potential game-changers for implantable devices. Pacemakers, neural stimulators, and insulin pumps currently require surgical replacement every 5 to 10 years, primarily due to battery limitations. Several medical device manufacturers have established development partnerships with diamond battery producers, with the first human trials of a diamond battery-powered health monitor expected to begin in late 2025 following regulatory approval. IoT, Internet of Things, applications represent another promising frontier, particularly for specialty applications like sensors and electronics in remote locations. The proliferation of remote sensors monitoring everything from infrastructure to environmental conditions creates millions of devices requiring power in locations where replacement is difficult or impossible. A major industrial sensor company has already redesigned several products to accommodate diamond batteries, targeting applications like bridge structural monitoring and remote pipeline sensing. Consumer electronics companies are exploring more limited applications where the battery's benefits justify their premium cost. Luxury watch manufacturers have emerged as unexpected early adopters, with several high-end brands developing concept timepieces powered by diamond batteries, marketing them as watches that could be passed down for generations without ever needing battery replacement. The financial world has taken notice of diamond battery technology, with investment accelerating dramatically over the past 18 months. Total venture capital funding in the sector exceeded $500 million in 2023, nearly triple the previous year's investment. Several specialized energy technology funds have established dedicated investment vehicles focused exclusively on this emerging field. Market analysis firm Bloomberg NEF projects the total addressable market for diamond batteries could reach $3.8 billion by 2030, focused primarily on high-value niche applications where the battery's unique attributes justify their premium cost. However, as manufacturing scales and costs decline, that market could expand dramatically to over $20 billion by 2035. What's driving this investor enthusiasm? The technology addresses multiple macro trends simultaneously: sustainable energy, circular economy principles through waste repurposing, and the growing demand for maintenance-free power solutions in our increasingly connected world. The economic implications extend beyond direct battery sales. The technology could create entirely new product categories designed around maintenance-free power supplies. It might also disrupt existing battery replacement service markets while creating new opportunities in manufacturing and isotope processing. Governments have also recognized the strategic importance of this technology. The UK has established a $75 million innovation fund specifically targeting diamond battery development, while the US Department of Energy recently announced a research initiative focused on advancing isotope processing techniques critical to the technology. Despite the tremendous potential, legitimate questions about safety naturally arise when discussing nuclear technology. However, the reality differs substantially from public perception. Diamond batteries contain minimal radioactive material, and the diamond structure itself acts as an exceptionally effective containment mechanism. Independent safety assessments have confirmed that properly manufactured diamond batteries emit less radiation than many naturally occurring materials. The beta particles generated during carbon-14 decay cannot penetrate the diamond structure, much less human skin. In fact, you would receive more radiation exposure from eating a banana, which contains naturally occurring potassium-40, than from holding a diamond battery. Nuclear batteries are not as dangerous as they seem. Regulatory frameworks are evolving to address this novel technology. The Nuclear Regulatory Commission in the US has established a specialized committee to develop appropriate guidelines, while international bodies like the IAEA have begun integrating diamond batteries into their existing frameworks for sealed radioactive sources. Several companies have proactively engaged with regulators, providing extensive testing data and safety analyses to establish appropriate protocols. This collaborative approach has accelerated the regulatory process while ensuring rigorous safety standards. Public perception remains a challenge, though. The word nuclear triggers automatic concern for many people regardless of the actual safety profile. Companies in the space have recognized this communication challenge and developed extensive educational materials explaining the technology's safety in accessible terms. While the technology shows immense promise, significant manufacturing challenges must be overcome to reach commercial scale. Diamond synthesis, particularly with radioactive carbon, requires specialized equipment and expertise. Currently, production capacity remains limited to hundreds or thousands of units, far below what mass-market applications would require. Supply chain considerations present another hurdle. Carbon-14 must be extracted from nuclear waste or produced in specialized reactors, requiring complex processing and handling. Companies have adopted various approaches to secure their isotope supply, from partnerships with nuclear facilities to developing proprietary extraction methods. Quality control presents unique challenges in this field. Every battery must be rigorously tested for both performance and safety, requiring specialized instrumentation and protocols. Several companies have developed automated testing systems to maintain consistency while increasing production volume. The good news is that significant progress is being made. NDB's pilot production facility in California represents a major advance in automated manufacturing techniques. Similarly, Arconlight's new UK facility incorporates custom-designed production equipment that increases throughput while maintaining precision. Economies of scale should eventually reduce costs substantially. Early prototypes cost thousands of dollars each to produce. But industry analysts project that mass production could eventually bring costs down to tens or hundreds of dollars per unit, still premium priced compared to conventional batteries, but justified by their extraordinary lifespan for many applications. Competitor technologies, diamond batteries, aren't developing in isolation. Several alternative long-life battery technologies are simultaneously advancing, creating a complex competitive landscape. Solid-state batteries represent perhaps the most direct competition in certain applications, offering improved energy density and longer lifespans than traditional lithium-ion, though still measured in years rather than decades. Beta-voltaic batteries, using different materials than diamond, have been under development for decades. These alternatives typically use semiconductor materials like silicon or gallium arsenide to convert radiation to electricity. While generally less efficient and durable than diamond-based designs, they can be less expensive to manufacture. Some companies are pursuing alternative radioisotopes. Tritium-based power sources offer higher power density but shorter lifespans, about 12 years, potentially better suited for applications requiring more power but not multi-decade operation. Others are exploring nickel-63, which offers a 100-year half-life and different performance characteristics. Thermal approaches present another alternative path. Radioisotope thermoelectric generators, RTGs, convert heat from radioactive decay directly to electricity. While bulkier and less efficient than beta-voltaic approaches, this proven technology has powered space missions for decades and is finding new terrestrial applications. How do diamond batteries compare? Their primary advantage remains their unmatched lifespan and stability. While other technologies might offer higher power output or lower initial cost, none can match the extraordinary durability of diamond batteries. This creates a natural market segmentation, with each technology finding its optimal application space. As we approach 2025, the commercial strategies of key players are coming into focus. NDB has announced plans for their first commercial product release in Q2 2025, a specialized battery targeted at industrial IoT applications, with pricing estimated at $500 per unit. They are positioning this initial offering for high-value applications where battery replacement is particularly problematic. Arcanite has outlined a different approach, focusing first on scientific instrumentation. Their initial product line, scheduled for release in mid-2025, will power environmental monitoring equipment designed for extreme conditions. This targeted strategy allows them to demonstrate value in controlled applications while scaling production capability. Both companies have indicated they are pursuing a premium pricing strategy, initially focusing on applications where the total cost of ownership over the device lifetime clearly favors their technology despite higher upfront costs. As manufacturing capacity increases, more price-sensitive markets will become viable targets. Distribution partnerships have become a key focus. Several companies have established agreements with specialized industrial suppliers rather than pursuing direct consumer sales. This approach leverages existing relationships in target industries while providing education and support through knowledgeable partners. Geographic prioritization reflects both regulatory environments and target applications. North American and European markets are receiving initial focus due to their more developed regulatory frameworks and concentration of high-value industrial and medical applications. Asian markets, particularly Japan with its established electronics industry, represent the next expansion priority. Marketing strategies emphasize total value rather than initial price. Companies are developing sophisticated calculation tools that demonstrate life cycle costs compared to conventional batteries, particularly highlighting applications where battery replacement is expensive or disruptive. These value demonstrations are proving crucial in converting interest to purchase commitments. Subscribe now and become a part of Expedition Diaries for more.